Okay, alright. So, how the buffer works when we add small amount of strong acid and strong base. Okay, a buffer works because large amount of acidic and basic. So this is acidic means component weak acid, and basic component conjugate base consume small amount of the added hydroxide or hydronium ion respectively. Okay, consider what happened in a solution containing high concentration of acetic acid, CH3COH, the component of weak acid, and its conjugate base from the salts, high concentration, when we add small amount of strong acid or base. Okay, let's focus first on the dissociation of the acid. Okay, we can write the dissociation of acid. Okay, this is the from the dissociation of acid here. Okay, we write the Ka. So Ka equal to the concentration of the acetate times the hydronium ion concentration divided by the acetic acid concentration. Okay, so Ka is constant, of course. What changing is these three components. Okay, now let's focus on the hydronium ion concentration. Alright, because the hydronium ion represents the pH. Okay, which is equal to, alright, we rearrange this, equal to Ka times with the concentration of the acid divided by the concentration of the conjugate base. Alright, acetate ion. Okay, so here, since Ka is constant, Ka is not changed as long as temperature not changed. So Ka value is constant. So hydronium ion concentration, the hydronium ion of the solutions depend on the buffer component concentration ratio. Means changing the component ratio here, the ratio of the component here, make the hydronium ion change. Ka is not changed. Alright. So when we add strong acid and strong base, this component change, the concentration ratio. So as this change, then concentration of the hydronium ion change. So if the ratio of weak acid and conjugate base goes up, mean more acid, less conjugate base, then hydronium ion concentration goes up. If the ratio of component acid and conjugate base goes down, mean less acid, more conjugate base, then the hydronium ion concentration goes down too. Alright. Okay, let's track this ratio as we add strong acid or strong base to a buffer, in which in this case we make the concentration ratio, we make the concentration of the component acid and component base equal. So means we set up, right, we make the concentration of the acid and the concentration of the conjugate base, mean concentration of the salts here, equal. For example, 1 molar acetic acid and 1 molar sodium acetate present in the buffer solution. Then what happens when we add strong acid or strong base to this buffer? Okay, figure 19.3 in the middle. We look at the figures. This is the figure, right? Okay, this is the figure. In the middle here, this is the buffer solution at initials. Here, we set up the concentration of both of them. Both of them are equal. The acetic acid and the salts concentration are equals. So conjugate base are equal to the weak acid. Okay. Then we add strong acid. Okay, when we add small amount of strong acid, of course, this strong acid produce hydronium ion, correct? And this hydronium ion react with an equal amount of acetate ion, the conjugate base. The hydronium ion from the strong acid will react with the equal amount of acetate ion from the buffer to form more acetate. Here, this is the equation. The hydronium ion from the added strong acid react with the acetate ion from the buffer, right? Then they produce acid, CH3COOH plus H2O. As a result, now what happened to the acetate ion concentration? So acetate ion concentration goes down by that small amount. And what happened to the concentration of the CH3COH? The concentration of CH3COH goes up by that amount. which increase the buffer component concentration ratio. Figure 19.3 to the left. Okay, here, when we add the small amount of a strong acid, right? So the conjugate base react with the added acid, right? So of course the conjugate base concentration goes down, right? And the concentration of acetic acid goes up. The component acid goes up. So in the process, as this react with the hydronium ion, it produces a small amount of CH3OH. Plus with the CH3COH originally present in the buffer, then increase like this. So overall ratio here goes up. Alright. When goes up, right? When the the concentration ratio goes up, then of course the hydronium ion goes up slightly. The hydronium ion increase very slightly. This goes up, Ka is constant, so overall you get goes up slightly. Okay, goes up slightly. Okay, what if we add strong base into the strong base sodium hydroxide, for example, right? Into the buffer solution. So then the addition of small amount of strong base produce the opposite result. The hydroxide ion from the added strong base react with an equal stoichiometric amount of acetic acid from the buffer. So then what happened? It produce produce acetate and H2O. Remember, acidity is sodium hydroxide. In reaction, sodium hydroxide react with the acetic acid, it produce sodium acetate. So means the concentration of acetate ion increase. And concentration of the acetic acid decrease. When we add sodium hydroxide into the buffer, right, initially equal concentration. The hydroxide ion from the strong base added react with the component acid of the buffer. So here this component acid decrease slightly, whereas from the reaction you produce that the acetate ion. So the acetate ion increase slightly. So overall goes down. So when goes down, the concentration ratio decreases. The buffer component concentration decreases, which decrease the hydronium ion concentration slightly. That's why you see the pH increase slightly for this case. Okay, so that is happen when a buffer solution is added with strong acid or strong base. So before we discuss the sample problem, let's summarize. Okay, I summarize here. Okay, you can see this figure 19.4. Alright. Okay, this is summary of the effect of the added acid or base on the concentration of buffer components. Okay, initial buffer ratio, let's say X, right? X. So here pH is Y. So when we add strong acid, so the component of the conjugate base of the buffer react with the strong acid, right, to produce the HA, the weak acid, and water. So here concentration of HA increases, and then the conjugate base decreases. So final buffer ratio now, because HA over A minus, right? Final ratio here, it is greater than X, and pH lower than Y. Okay. If we add strong base, component acid of the buffer will react with the base, producing the conjugate base and water. So in this case, the component acid, weak acid decreases, and component of the base increases in the buffer. So final buffer ratio here now lower than X, so pH greater than 1. Okay, that summarize of the effect of added acid or base on the concentration of buffer components. Okay, then before I discuss the sample problem, I want to introduce here Henderson-Hasselbalch equation. For any weak acid, the dissociation and K expression is given, and you know this already. So the key variable that determine the ion concentration is the concentration ratio of acid species to the base species. So as before, rearrange it, you get this. Alright, hydronium ion equal to Ka times the concentration ratio. Right, conjugate acid and conjugate base of the buffer. Okay, if they put negative log on this equation, so means negative log hydronium ion equal to negative log Ka, right, plus negative log, actually this is plus, right, times mean plus time negative, because negative log, right, so you get negative. So here negative log concentration of acid and divide by concentration of the conjugate base. So negative log hydronium ion mean pH, negative log Ka mean pKa. So this is remain negative log concentration of acid over conjugate base. Okay, if we change the sign, we want to make it positive, so we inverse the ratio. Inverse the ratio A minus over HA. So pH equal to pKa plus log concentration of the conjugate base over the concentration of the acid. We can use this equation to solve the problems. Any problem involving buffer acid base react with any strong acid or strong base. Let's use this Henderson-Hasselbalch equation to solve problems. Okay, I give you a sample problem here. We can look in the PowerPoint that I have shared to you about acid base part 2. Okay. Calculating the effect of added hydronium ion, I mean from the strong acid or hydroxide ion, strong base, on buffer pH. So calculate the pH. A buffer solution consisting of 0.5 molar HClO and 0.6 molar NaClO, the salts, its salts. Okay, weak acid, ClO minus, right, is the conjugate base. Given here for the acid 2.9 times 10 negative 8. We calculate the pH after adding 0.02 mole of solid sodium hydroxide to 1 liter of the buffer solution in part A. Alright. Assume the addition of sodium hydroxide causes negligible volume change. We adding sodium hydroxide, strong base. C, pH after adding 0.02 mole hydrochloric acid, strong acid, to 1 liter of the buffer solution in part A. Assume that the addition of the HCl causes negligible volume change. Okay, for this is quite direct. Okay, we look at the A, solution for A. Okay, you have a solution A, you have you have the concentration of the HClO and the concentration of the NaClO. So using Henderson-Hasselbalch equation, this is the Henderson-Hasselbalch. pH equal to pKa plus log salt over acid. Salt here is the concentration of ClO or similar to NaClO, and acid HClO. Alright, so you have the Ka. Ka is given, so negative log 2.9 times 10 negative 8, 2.9 times 10 negative 8 plus log, okay, the salt is given, concentration 0.6, and then the base, the acid 0.5. So then you get 7.62. Alright. Okay, now calculate the pH after adding 0.02 mole of solid sodium hydroxide to 1 liter of the buffer solution in part A. So here, this is strong base, means if you add 0.02 mole solid sodium hydroxide, it produces similar amount of hydroxide ion, which is 0.02 mole. So what is the concentration of the hydroxide ion? Okay, mole, 0.02 mole divided by 1 liter, you get 0.02 molar. So that is the concentration of the hydroxide ion. Okay, so we look at the solution. Okay, now we have the reaction table. We plug in the reaction table. Alright, at initial, this is the buffer solution. Alright, you have the initial concentration of the acid, HClO 0.5 and ClO minus 0.6. Then you add the hydroxide ion, correct? Hydroxide ion, this is the concentration. You add with 0.02. Alright, at initial, this is the added 0.02 molar sodium hydroxide. Then the reaction occurs. Of course, this is the limiting reactant. This is the limiting reactant, hydroxide ion. So equal concentration of HClO reacted with the hydroxide ion, which is negative 0.02. Right, because this hydroxide ion is limiting reactant. So 0.02. Neutralization. This is the neutralization. Then of course it produces plus 0.02 plus 0.02 equal ratio here. You see 1 to 1 to 1, so means plus 0.02. So at the final you have 0.48 remaining of acid. Right, slight decrease you can see. For hydroxide ion 0, no more. For ClO minus increased by 0.62. Right. So you have the final concentration for the weak acid and its conjugate base. So you plug into the Henderson-Hasselbalch equation. pH equal to pK plus log salt over acid. So here pH equal to negative log 2.9 times 10 negative 8 plus log 0.62. Right, for the salts divided by the weak acid 0.48. So that you have 7.66. Alright, so adding hydroxide ion increase slightly the concentration of the buffer solution. Before this is, you can see 7.62. Alright, so when you add the base, right, 0.02 molar, then it is increased slightly to 7.66. Okay, now we look at the solution for C. Calculate the pH after adding 0.02 mole of HCl to 1 liter of the buffer solution in part A. Assume that the addition of HCl causes negligible volume change. Okay. First, we calculate the concentration of hydronium added. Okay, it is 0.02 mole. 0.02 mole of HCl. That means it produces 0.02 mole of hydronium ion. Okay. Then it's added into 1 liter buffer solution. So what is the concentration? 0.02 mole divided by 1 liter, you get 0.02 molar hydronium ion. So that is the concentration of the hydronium ion added. Okay, hydronium ion added. Then we plug in into the reaction table. Okay, at initial you have 0.6. This is the buffer solution concentration, 0.06 ClO minus conjugate base and the 0.5 molar HClO. Alright, so the reaction is between the conjugate base with the hydronium ion added. Okay, I write here SH plus. Actually, this is H3O plus. Okay, same. Okay, so this is 0. This is 0.02. All right. So change occurs. Okay, this is the limiting reactants. Of course, equal molar of ClO and reacted with the 0.02 H plus equal molar of ClO. So negative 0.02. All right. So for H plus, it consumes all 0.02. And then for the ClO, because the reaction produced, of course, it produce net positive 0.02. Increase by 0.0 produce. Okay, then at final, what is the remaining conjugate base concentration is 0.58. This is 0, right? H plus, no, that is limiting reactant, and the final concentration of conjugate acid is 0.52. Okay, So we want to calculate the pH. So plug in the Henderson-Hasselbalch equation. pH equal to pKa plus log salt over acid. So pH equal to negative log 2.9 times 10 negative 8 pKa of the acid plus log 0.58 divided by 0.5 to the salts and its conjugate acid. So you get 0.59. So from here we see addition of strong acid and just now decrease the pH slightly. Originally, the buffer solution is 7.62. Now it decreased slightly when acid is added into it. 7.59.